What if I told you that the average value of current in your toaster is 0, even as it's browning your toast? Or that the warning sign on a power substation should actually say, danger, 0 average voltage? These absurd results are exactly what we get if we take a naive approach to averaging current and voltage in AC circuits. So in this video, we're going to figure out exactly what's going wrong here and how to fix it. And unlike your introductory physics book, I'm going to tell the whole story here, including all the details of the calculus we need to develop a meaningful way of averaging current and voltage. And that's what we call RMS, or root mean square averaging. And just a quick note here before we get started, this video is timestamped into chapters if you need to skip to a particular section. So to get started, recall that in AC circuits, we drive the circuit with a sinusoidal voltage, and we see a sinusoidal current oscillating back and forth in the circuit, and the voltage and current are not necessarily in phase with each other. So just to be general here, we usually say that the current, little I of t, is given by big I cosine omega t, where big I is the current amplitude. And we call our voltage function little v of t, and that's given by big V times cosine omega t plus phi, where big V is the voltage amplitude and phi is the phase angle. So that's the phase difference between the current and voltage functions. And we can see that up here in the graph of the current and the voltage. Those are two sinusoidal functions that are out of phase with each other, but they have the same period. So these are just general statements that are true for any AC circuit. And that's why we have this black box approach to the circuit over here on the left. We just have some network of unknown circuit elements in there, some combination of resistors, capacitors, and inductors, but we know the voltage and current are both sinusoidal and have the same frequency. So the main goal of this video is to develop a meaningful approach to time averaging the voltage and current for an AC circuit, and this isn't as straightforward as you might guess. The naive approach to averaging actually turns out to be useless. So let's start with that naive approach, see what goes wrong, and then find a way to fix it. And that turns out to be RMS, or root mean square averaging. So we start with a quick review of the calculus here. What does it mean to find the average value of a function f of x on an interval a to b? Well, the average value has a geometric meaning. It's the constant function bounding the same area as f of x on the interval a to b. So this constant function f bar is the special y value that bounds exactly the same area as f on a given interval. And I hope this makes some intuitive sense as an average. For example, if we're looking at a velocity time graph, the bounded area would be total displacement, and the average velocity would be the constant velocity that covers the same displacement in the same amount of time. So this geometric meaning of average allows us to quickly find a formula for computing average values. We just set the area of the rectangle equal to the area under the original curve. So we'll call those areas A1 and A2, and now we're setting them equal. And so the area under the rectangle is just length times height, and the area under the curve is a definite integral of f of x from a to b. So note there that the length of the rectangle was b minus a, so on the left side we just have height times length to get that area. All we have to do now is divide by b minus a, and we've got a formula for the average value of a function. So f bar is 1 over b minus a, the interval width, times the definite integral from a to b of f of x dx. That's the area bounded by the function on the given interval. So that's the calculus review on averages. Now let's apply this to averaging sinusoidal functions. So to start things out, I want to clarify that we're talking about long-run averages here. So for AC circuits, we're generally averaging over thousands of periods of a sinusoidal voltage or current function. So the first thing we need to knock out here is how to pick the right interval for averaging our periodic functions. So I'm going to start by just making a claim that turns out to be mostly true. So I'm claiming that for any periodic function, the long-run average can be calculated by getting the average over just one period. And I'm also suggesting that this isn't precisely true, but trust me for a minute, it becomes arbitrarily close to true in the large time limit. In other words, if we're averaging over many cycles of the function. So while you're still in the mood to give me the benefit of the doubt, let's look at what happens when we average over one period. And note there that the period of this function, a cosine omega t, is just 2 pi divided by omega. That omega is the coefficient of t. And we can already see geometrically what's going to happen. The signed area bounded by this graph on one period is 0 by symmetry. So the average value must be 0 on one period and also in the long run, which makes a lot of sense. That's the midline of a sinusoidal function, and it spends just as much time above and below that value, so the average value should be 0. Now we can also justify this with an integral, and there we've just used our formula for the average value of a function. I have 1 divided by the interval width, and that's a 2 pi over omega, the length of one period, and then we integrate from 0 to the end of the first period to get that signed area bounded by the function. So now we're going to factor out the a and guess the antiderivative of that cosine omega t piece. And note that the chain rule produced a 1 over omega when we guessed that antiderivative. So I have an a over omega out in front of the sine omega t. Now the omegas are going to cancel here, giving me an a over 2 pi, and I evaluate across the limits of integration. So subbing in that upper limit of t equals 2 pi over omega, the omegas cancel, and I get sine 2 pi. And when I sub in the lower limit, I get the sine of 0. Well, the sine of 2 pi and the sine of 0 are both 0. And as we expected, our average value over one period turned out to be 0. So let's get back to that tiny problem with my claim about averaging periodic functions. This all seems intuitively obvious because the average value on the first period is the same as the average value on the second period and the nth period and so on. But our claim is actually a little bit flawed, because if I'm averaging over a long period of time, say thousands of periods, but my time interval doesn't neatly cover an integer number of periods, we can end up with a little tag end on the area calculation just past the completion of a period. And the way I've shown it in the graph, that's a positive contribution, and that makes the result for the average value integral slightly bigger than 0. Or we could advance a little farther than that and end up with a net negative result for our average value integral, because we're integrating over a little more than half that final period and therefore capturing a slight net negative area. But the point is, if I'm averaging over a large period of time, and I'm just calling the time interval tau there, the denominator in the average value integral is growing to infinity. And these little tag end errors, they're always staying finite. So bottom line, the large time limit of the average value integral is just equal to the average value over one period. In other words, the tiny bit of error that we incur from capturing a fraction of a period at the very end becomes negligible in the large time limit. So let's just extract ourselves from calculus land real quick and ask what this actually means for current and voltage functions in AC circuits. If we average the current function, that's the average over one period of a simple cosine function. And we already know that vanishes, so the average current must be 0. So now we can show the details for the sake of completeness here, but the terrain is familiar. There's our standard current function, I cosine omega t. Note that it's standard to give that a phase angle of 0. So we write down the average value integral, and we're just going to integrate over the first period of the function there. Again, the length of that period is 2 pi over omega, so I have a 1 over 2 pi over omega out in front, and I integrate from 0 to 2 pi over omega. And we're going to factor out the I and guess the antiderivative of cosine omega t, which is 1 over omega sine omega t. And now these omegas are going to cancel each other out. But of course, the bigger deal is that when we sub in the upper and lower limits for t, that sine function is going to vanish at both the upper and lower limits. So I have a sine of 2 pi, which is 0, minus a sine of 0, which is also 0, and I get 0 for the average current. And the same thing occurs for the voltage function. Now that's a little different because of that phase angle. So check this out. I set up my average value integral, and everything looks practically the same there. And when I guess the antiderivative of cosine omega t plus phi, that's just a 1 over omega sine omega t plus phi. And now when I sub in my upper and lower limits into that sine function, the argument is just a little more nuanced. When I sub in the 2 pi over omega for t, I get a sine of 2 pi plus phi. And when I sub in the 0 for t, I get a sine of phi. And now to simplify this, we have to make a periodicity argument. We remember that the sine function is a periodic function with a period of 2 pi. And that means if we take the sine of x plus 2 pi, that's the same as the sine of x. So by using the periodicity of the sine function, we can see that this difference here in the parentheses, sine of 2 pi plus phi minus sine of phi, must vanish. So our average voltage is also 0. But is this really what we want to mean by average current and voltage in an AC circuit? As I pointed out in the intro, this would mean power substations would have warning signs that say, danger, 0 average voltage. This is clearly the wrong way to do things, and that's where RMS averaging comes to the rescue. So the issue with standard averaging is that sinusoidal functions spend just as much time below the t-axis as they do above, giving us the useless average of 0. So we're going to start with our current function here, and there is just a basic cosine. And you can tell just at a glance from the shaded area that when we average over one period, we're going to get 0. Now we can fix this issue by squaring the function, forcing every point to be positive. So here's the square of the current function. And note that a period of a squared sine or cosine is actually half as much as the period of the original function. But we can average over one period or two periods without changing the result for the average, and I prefer to just use the same limits of integration and average over 2 periods. So that's what I've got shaded in on the graph. So here's what we're going to do. We average the squared function so we can get a non-zero result and a meaningful measure of how much current is moving in our circuit. Note there that the denominator in that average value integral was 2 pi over omega, but I went ahead and simplified to omega over 2 pi in front of the integral. So now we take the square root of that result to compensate for the squaring we did before we integrated. And note in particular, this is going to get us back to units of amps for the current. And this is what we call an RMS average, standing for root mean square, because we're taking the root of the mean, in other words, the average, of the square of the function. So plugging in our integral for the average value of the square of the function, there it is, the formula for RMS current. Now, of course, we're going to do the same thing for voltage, but this time I'll go a little bit faster. There's our original voltage function, and note the phase shift there. This is not a pure sine or a pure cosine. It's starting at some arbitrary point determined by the phase shift phi. And I've shaded in our first period, and I can still tell that the net signed area on that first period is 0, so the average value of the voltage function is 0. So we square it. And the amplitude of my squared voltage function is v squared. And I can see that it has a period half as much as the period of the original voltage function. And we're going to integrate over 2 periods, just because that's my preference, just to keep the limits of integration the same. And so we take the average value of the square of the voltage function. Then we compensate by square rooting the result, and that gives us back the original units of volts here. And then we sub in our average value integral from the first line, and we get this huge formula for the RMS voltage. So now we have these big formulas for RMS current and voltage, and it's time to actually perform these integrals. And the whole point of these calculations is to relate the RMS values to the original amplitude values, the big I and big V. So we start with the RMS current calculation, and we immediately recognize this integral. This is a really common type of trigonometric integral where I have an integral essentially of just cosine squared. Now the only way around this thing is to use this clever identity for the square of a cosine function. It turns out to be 1/2 times the quantity 1 plus the cosine of twice the angle. Well, our angle here is omega t. So when we apply that identity, remember there was a 1/2 out in front of it. So now out in front of this integral, I have a 4 down there in the denominator, just absorbing that 1/2. And then I'm integrating 1 plus a cosine of twice the original angle. So now the antiderivative of each of these pieces is quickly guessable. The antiderivative of 1 is just going to be t, and the antiderivative of cosine 2 omega t is just 1 over 2 omega sine 2 omega t. So now we think about subbing in these limits of integration. And just starting with the 0 down there at the bottom, if I sub in 0 for t, both of these terms vanish. So I'm not worried about that at all. And then I look at the upper limit, 2 pi over omega, and I notice if I sub that in for t in my sine function, that's going to give me a sine of 4 pi, which I know is 0. So the only survivor here is when I sub the upper limit in for that t that's hanging around out in front. And so things are starting to get simple. I have the square root of omega I squared over 4 pi, then multiplied by 2 pi over omega. And we can cancel a factor of 2 pi, and we can cancel the omegas. And this gives us the square root of I squared divided by 2. And when I take the square root, we get our final answer. The RMS current is just equal to the original current amplitude, big I, divided by the square root of 2. So again, we're going to repeat the calculation for the voltage function, but just move a little bit faster through it. And it's worth looking at because of how the phase angle complicates things a little bit. So there's our RMS value integral. Again, that's the average value integral of the square of the original function, then square rooted. And again, it's a classic trigonometric integral with the square of a cosine function, and we apply the usual identity, and we absorbed a 1/2 out in front there, and the integral splits into a 1 plus cosine of twice the original angle, so 2 times the quantity omega t plus phi. Now we need to guess the antiderivatives. And for the 1, of course, that's just a t. And for that cosine piece, it's going to be, again, a 1 over 2 omega, then times the sine of that original angle, 2 times the quantity omega t plus phi. Now, if that antiderivative is troubling you, just try taking the derivative of it. And notice that I distributed in there. So my t-containing term is 2 omega t. When I take the derivative, the chain rule produces a factor of the derivative of the interior function, which is just 2 omega. And that 2 omega is there out in front waiting to cancel it. So that's how we get back to the original function. So now I'm subbing in the limits of integration, but things aren't as simple this time. If we just kind of preview what's going to happen when we sub in t equals 0, well, this leading term dies just like it did last time. But when I sub in t equals 0 to my sine function, I still end up with a sine of 2 phi. Then think about the upper limit. Of course, when I sub that in for t, I get a 2 pi over omega. But when I sub that in for the sine function, I end up with the sine of 4 pi plus 2 phi. So when we evaluate across those limits of integration and factor out the 1 over 2 omega, this is what happens to the trig function part of it. I end up with a sine of 4 pi plus 2 phi minus the sine of 2 phi. And so again, we have to make a periodicity argument. The sine function is a periodic function with period 2 pi. That means it also has a period of 4 pi. It just repeats every 4 pi units. So the value of the sine function at a location of 2 phi has to be the same as the value of the sine function at 4 pi plus 2 phi. And so the difference between those two has to be 0. So again, evaluating across the limits of integration, the trig piece vanishes. The t out in front vanishes when I sub in the lower limit of 0. And the only survivor here is when we sub in 2 pi over omega for t. So there we have it. And now we can cancel the factors of omega and a factor of 2 pi. That gives us square root v squared over 2. And we take the square root. And we get basically the same result. The RMS voltage is going to be the voltage amplitude for this sinusoidal voltage function divided by the square root of 2. So now that we have these nice formulas relating RMS values and amplitude, let's wrap things up with a really quick example about residential wiring. So here's our example. We're told that we're using a multimeter set to AC voltage, and we plug the leads into a wall outlet and we get a reading of 114 volts AC. Now, knowing that multimeters actually tell you the RMS values of voltage and current. And by the way, that's a super important thing to remember in the physics lab. The multimeter is always telling you RMS values. We're asked to find the peak voltage at the outlet. In other words, the voltage amplitude. So this is a ridiculously fast calculation. I'm really just asking about this relationship between voltage amplitude and RMS voltage. And what we know this time is the RMS value, and what we're looking for is the voltage amplitude. So we just have to multiply both sides by square root of 2, and my voltage amplitude is going to be root 2 times the RMS voltage. But we were told that was 114 volts, and we crunched the numbers in our calculator, and this yields a voltage amplitude of 161.2 volts. And we're done. This video is part of a short series on AC circuits, and you can find links to all those videos down there in the description. In the next video, we learn how to compute average power for resistors, capacitors, and inductors. And we're going to relate the average power dissipated by a resistor to the RMS values of current and voltage. And this is actually where we see a nice payoff to all this RMS stuff, because average power turns out to be RMS current multiplied by RMS voltage for the resistor. In other words, we get an analogous relationship to what we already saw for direct current circuits. I'll post a link to that video at the upper left, and I'll see you there.